to make our lives a little easier, if there's a bunch of tables in the book, I've copied them. So we're going to use these today. Got to talk about custodian about pushing you guys closer. Okay. So where I got some of these tables from, the one for entropy, I got from the back of your book, page 407. So you can see that the first column was the heats of formation that we used earlier to find enthalpy. The second column is the entropy something has. The entropy it has at 25 degrees Celsius, 1 atmosphere. So that's the second column. We'll talk about the third column in just a little bit. Okay. So standard entropy is the entropy at 25 degrees Celsius, 1 atmosphere pressure. Standard, we picked when we're going to measure enthalpy. Entropy. Randomness. So because it's standard, we put the symbol for entropy is S. Put the little degree sign to say it's standard. And the units are right there on the top. It's joules divided by Kelvin. That's the units for entropy. S degree, like a degree sign, but that little degree sign means standard. And somebody picked 0. Okay. So because entropy, with this we'll be able to look up the entropy of the reactants, because they'll be on the list, and we'll be able to look up the entropy of the products, we can find the change in entropy. Just like we did the change in enthalpy, we can do products minus reactants. Do products minus reactants. And that will tell us the entropy. And the sign of that entropy will tell us whether that reaction is spontaneous, whether that reaction is going to happen, or whether it's going to tend to happen, whether it's in favor of it or opposed to it. Because entropy tends to go up, so we're looking for a positive entropy change. If it's positive, that's in favor of it happening. If it's negative, it's opposed to it happening.
Oh, so
Decrease, yeah. Entropy decrease is not favorable. Entropy increase is favorable. Both can happen. Okay? So if I wanted to calculate the standard entropy for this reaction, CH4 plus 2O2 makes CO2 plus 2H2O gas. So the one that, the entropy change from the flame coming out of the Bunsen burner. And yesterday we learned how to predict. Here, we're not going to be able to predict this very well, because this has 3 pieces and that has 3 pieces, right? So the number of pieces didn't change. The reactants start off with 3 gases. The products end up with 3 gases. So that didn't change very much. So I'm not expecting the entropy to change very much here. And I can't tell what's going to be positive or negative, but I know it's not going to be very big. Does that make sense? And so what I need to do is look up all those numbers. So I did. So I looked up CH4. Next to CH4, it said 186.2 kilojoules or joules per Kelvin mole. For O2, it went down to O2 and it was 205.0. For CO2, it was 213.6. And for H2O, it was 187.7. Everybody okay? That's where I got those numbers from? Just looked them up off the table. Okay. So to find the change in entropy, I need the entropy of the products minus the entropy of the reactants. So the products are CO2 and H2O. So the number for CO2 was 213.6 joules per Kelvin. Plus the number for H2O. When I looked up H2O, I had to look up the H2O gas, not the H2O liquid. And the H2O, there was 2 of them, so I'm going to have to multiply that number by 2. And from that, I need to subtract the reactants, CH4, and I need to subtract twice the number for oxygen. Notice I subtract both those ones at the end. And if you push those buttons, 213.6 plus 2 times 188.7 minus 186.2 minus 2 times 205 equals, I got negative 5.2. Negative 5.2 joules per Kelvin. So the math is the same as finding out delta H, products minus reactants. The mistake people make is not doing products first and forgetting the coefficients. Notice it didn't change very much. Okay, is that entropy change favorable or unfavorable? Unfavorable because it's negative. But we know that this reaction, the delta H for this is flame. The delta H for this is going to be negative. Right? It's got to be exothermic. And yesterday we said exothermic was favorable. Right? That things fall downhill. So in terms of energy, it's favorable for this to happen. In terms of entropy, it's unfavorable. Okay? Which one wins? We'll figure out how to figure that out later. But we got entropy is in favor of if it goes up. Enthalpy is in favor if it goes down. So I got 2 things I got to worry about if I'm worried about spontaneity. Okay? 2 things. So remember, a spontaneous reaction is one that will happen. Doesn't say how fast it'll happen. You don't have to do anything to make it happen. If you have those conditions, this reaction will happen. The name for reactions that don't happen is non-spontaneous. I don't want you to get this confused with how fast it happens. If you do the math, you will see that rust forming is spontaneous, but it can happen really slowly, or it can happen really fast. So if I want to see if it's spontaneous, I need to look at both heat and disorder, enthalpy and entropy. Heat and entropy. It does, aluminum oxides, but what aluminum does is when it makes its rust is clear and it sticks to the aluminum. So you get a coating of rust all the way across the top that doesn't flake off. So when you scratch a piece of aluminum, you'll see it's shinier underneath. That's because they've got that oxide coating. Rust is dangerous. Rust is a problem because it flakes off. It exposes more metal, so it can rust. So aluminum stops itself from rusting by putting a coat over the top of it. Yeah, rust is just oxidized. Okay, so I need to look at those two. And we said exothermic reactions tend to be spontaneous. They're going to have a negative delta H. If it's negative delta H, it's in favor. Because if I start with this much energy and end up with lower energy, I've gone downhill, just like the bowling ball falling off the shelf. That bowling ball will fall off the shelf, we just don't know how soon. Yep, has a positive S. So reactions where the entropy of the products is bigger than the reactants. Then if you did products minus reactants, you'd be taking a big number and subtracting a smaller number. You would end up with a positive delta S. Exothermic is delta H is negative. Okay, with S we can't use the word therm because it's not heat. Okay, so there is no word to say positive delta S. Okay, you can't say endoentric. It doesn't work. Okay. So a change with positive delta S and negative delta H is always spontaneous because it's got both things in favor of it happening. Heat makes it happen, entropy makes it happen, it's going to happen. If everything's in favor of it happening, it's going to happen. A change with the opposite signs. A negative delta S and a positive delta H is never spontaneous. If you want that to happen, you have to do something else to it. You have to put energy into it. Usually is how you make it happen. But so that means to figure out whether a reaction is going to be spontaneous, we need to do products minus reactants with delta H. We need to do products minus reactants with delta S and look at those two numbers. Okay? Do you want to look at two numbers when you're trying to decide whether a reaction is going to happen? I don't. I'd rather look at just one. And what do I do when one's in favor and one's opposed? How do I decide if it's going to be spontaneous then? Okay. So a scientist named Gibbs came up with a concept that combined those two ideas. And it's called Gibbs free energy. Much of this stuff came out of, they were trying to make the most efficient steam engine. Okay, because this was done in the late 1800s. So they're trying to see how you could get the most power out of the fuel you were burning and the steam you were making. How do you get the most power into your train? What's the most you can get? And so they were looking for the energy free to do work. And what Gibbs found was that if there was energy in that reaction that was free to do work, that reaction was spontaneous. That figuring out whether it was going to give off work told you whether it was going to happen or not. Okay? So, and this is how he calculated it. The symbol for Gibbs free energy is a capital G. And delta G equals delta H minus T delta S. The T has to be in Kelvin for it to work. Temperature in Kelvin. Temperature in Kelvin. Because yesterday we said ice melts with spontaneous, but that's not always true. Ice melts in this room because the temperature is high enough for it to melt. I take water and I put it in the freezer. Water freezes. Ice doesn't melt in the freezer. So temperature decides whether ice is going to melt or not. Right? And this equation tells us why. Because ice melting, you have to put heat in so delta H is positive. Right? But you're going from a solid to a liquid, so delta S is positive. If I got a positive number and a positive number, what's going to decide the sign of delta G is how big the temperature is. Is a positive minus a positive? Depends on how big they are, whether it's going to be a positive or negative number. Because 4 minus 3 is a positive one, but 3 minus 4 is a negative one. So it depends on the size, and temperature changes that second term. And all spontaneous reactions release free energy. And release means to give off. Since release means to give off, and I start off with so much free energy and I give off free energy, I ended up lower. So that's going to be a negative delta G. Delta G's got to be negative. If delta G is negative, that reaction is spontaneous. If delta G is positive, it is not spontaneous. One number tells us whether it's spontaneous or not. So if delta G is negative, it's spontaneous. But delta G is made up of those three pieces. So let's look at the signs of those three pieces and what it tells us about temperature. Okay? So I'm going to look and see how delta G, delta H, and delta S, what signs they have, and whether it's spontaneous. So if delta H is negative, and delta S is positive, what does the sign of delta G? Well, a negative minus a positive, negative 3 minus 4, it's got to be a negative number, right? No matter what numbers I stick in there. Negative 4 minus 3 is negative 7, still a negative number, right? So delta G will always be negative in this situation. The delta H is in favor, the delta S is in favor, so delta G is in favor. Well, that's what we're going to work out. So this is spontaneous at all temperatures. So that's what we're going to do. We're going to look at all the combinations and see where temperature makes a difference. So this will happen all the time because both pieces are in favor of it. The delta H says it's negative, it's downhill, that's going to happen, and it's messy. What happens is downhill and messy. Okay? What if they're both positive? Positive minus a positive, the temperature is going to make a difference, right? And if I want it to be spontaneous, I need it to be a negative number. So I need the second number to be bigger. I need to subtract a bigger number, right? So if it's going to be negative, it's only going to be negative at high temperatures. If I get the temperature high enough, this will happen. This is ice melting. We have to put heat in to melt ice, positive delta H, but we're going from liquid to solid to liquid, positive delta S, and if the temperature is high enough, ice will melt. If the temperature is not high enough, the ice won't melt. We call these reactions entropy driven. Because the thing that's in favor of it happening is the entropy. What if they're both negative? What if delta H and delta S are both negative? Negative 4 minus a negative 3 is negative 1, but negative 3 minus negative 4, positive 1, right? Negative 3 minus negative 4, that would be plus 4. That would get you a positive 1. Negative 4 minus negative 3 will get you a negative 1. So I want that, so it's not, it depends on the temperature, and I need the second term to have a small number if I want it to be spontaneous. So that's only going to happen at low temperature. We could use this, we could use ice freezing for this. Ice freezing has got to be exothermic, because you put heat in to melt it, you got to get heat back out when it freezes. And you're going from a liquid to a solid, so that's a positive. So liquid to a solid, so that's a negative entropy change. Entropy is going down, I'm going from messy to less messy. And ice only freezes if the temperature is low enough. Right? We call these enthalpy driven. With the driven words, all we're picking is which one's in favor of it happening. The enthalpy is in favor of it happening, so it's driven by the enthalpy. Here, the entropy is in favor of it happening, so that's entropy driven. Then you have the last case, a positive delta H and a negative delta S. So I'd have a positive minus a negative. Positive minus a negative is always going to be positive. So that means this won't happen at any temperature. Actually, it's worse than that. What you wrote is going to happen exactly backwards. Those products that you wrote will turn back into the reactants. If you have any of those products, they're not going to be there. They're going to turn back into the reactants. Because if it's positive this way, it's got to be negative that way. So let me tell you about my problems. Okay. So I'm going to use the numbers off this thermo table, and we're going to try to see whether that reaction is spontaneous. So I'm going to look up some numbers. I looked up the delta H's first. I looked up H2S, it was negative 20.1 kilojoules. O2 I looked up and it was 0 because it doesn't take any heat to make oxygen out of oxygen. The H2O was negative 285.8 kilojoules because it was the liquid one. Nope, no, we're looking at heats of formation. Heats of formation because we're trying to do heat first. We're doing the heat part first. Then we'll do the entropy part. So I'm using the ones here, the first column, the heat parts. And what we do with those numbers is products minus reactants. So look at those numbers. Do products minus reactants. Delta H equals 2 times the number for H2O liquid, starting with the products. And the H2O liquid was negative 285.8. Plus twice the number for sulfur. And that was 0. Minus twice the number for H2S. That was 20.1 minus the number for our oxygen, which was 0. And you push this, you push the buttons, and you get negative 531.4. That's negative, so delta H is in favor of this happening. Right? So this one, we know at least will happen if I get the temperature right. No matter what the entropy is, if I get the temperature right, I can make this happen because at least the enthalpy is in favor of it happening. Okay? Now I'm going to do the same thing for entropy. So I look up the second column on here. I got that from page 407. Okay? I look up H2S is 205.6. The O2 is 205.0. None of these are going to be zero entropy. They're all going to have some randomness. Actually, the third law of thermodynamics tells you what 0 is. 0 is a pure crystal, so everything's in neat orderly arrangement, at absolute 0. Since we can't get to absolute 0, there's nothing with 0 entropy. And the H2O was 69.94 kilojoules per Kelvin, and the S was 31.9 joules per Kelvin. So I just look those numbers up on the table. Got to be careful when I look at water. Always make sure you pick the one that matches the state that they gave you, because there's 2 numbers for water every time. Then you do products minus reactants. So to find the change in entropy, I take twice the number for water, 69.94 kilojoules, plus twice the number for sulfur, 31.9 joules per Kelvin, minus twice the number for H2S, 205.6, minus the number for oxygen, 205. Okay, so these had coefficients, so I had to use the coefficients.
But I mean, like, don't we have to do like first plus to get add both together, so like 2H2 H2S plus both, and then.
Okay, so you can do that, but it's more work because what you're talking about doing is basically putting parentheses here and here, and that turns that into a plus sign. Okay, you can do it that way, or you just remember I add up all of the products and subtract all the reactants. Okay, which is to me is easier. Add up all the products, subtract all the reactants, rather than adding twice and then subtracting. Okay? So I get negative 412.8. Delta S is not in favor of this happening. Delta H was in favor. Delta S is not. And we can see why. I went from gases to liquids and solids. The entropy is supposed to go down, right? So I've got 2 numbers. One's in favor of it, one's opposed to it. Is it spontaneous? Temperature is going to decide. So I have to stick it into the equation. Delta G equals delta H minus T delta S. So copying the numbers from the last 2 problems, we said delta H was negative 531.4 kilojoules. Right? Did that math, products minus reactants. Said delta S was negative 412.5 joules per Kelvin. And since we're at standard conditions, T is 25 degrees Celsius, and 25 degrees Celsius plus 273 equals 298 Kelvin. Because Celsius plus 273 gets me Kelvin. How do we get the Celsius? Because that little degree sign up top tells you that it's 25 degrees Celsius.
And why do we do plus 273?
Because I need it in Kelvin. Change Celsius to Kelvin, you add 273.
Oh.
Remember, Celsius and Kelvin are 273 apart. Kelvin's always bigger. Now, if you do that multiplication, you get this. I just multiplied 298 times negative 412.5. But I can't do that math right now because this one's in kilojoules and that one's only in joules. That is going to happen every time you use this equation because entropies are always reported in joules, enthalpies are always reported in kilojoules. Okay. So it's going to happen every time. So all you have to do is remember to change joules to kilojoules. You move the decimal point 3 times. So instead of writing negative 123,000 joules, I can write negative 123 kilojoules. I move the decimal point 1, 2, 3 to the left. There are two negative signs because one's a subtraction and one's the negative sign. See, I've just carried all these signs down. That's all I did. Okay, make sense? So now when I add those numbers, I get negative 408.4. Is this spontaneous?
Yes.
It is because this, when I finally got to the end, delta G was negative. If delta G is negative, it's spontaneous. Okay, a word for that is exergonic. And then there's endergonic. The G from Gibbs free energy, they tried to make into a word. I don't know why. I don't know how, but exergonic. So negative delta G, just like exothermic is negative delta H. Okay. Okay. So that's how you do those problems. Products minus reactants to find delta S. Products minus reactants to find delta H. Put those two together with delta G equals delta H minus T delta S. That decides whether it's spontaneous. Well, that would be the homework. Looks like this.